Hello everyone, Namaste. I am Ramnath who would like to present you the series on key learnings from chip development, part 4, which is on RTL design. Many of you might know that RTL design translates the chip architecture into abstract form to analyze the technology agnostic design implementation in great detail. That is why RTL design is the bridge between system specification and circuit implementation of the chip. Thanks for learning along with me. Feel free to provide your suggestions. Thank you. As we observed in the earlier video, system design specified in requirements and specification stage is translated into architectural design as part of the design making to bring more concreteness. The architectural design is then converted into RTL design to give more specificness of the design implementation. Briefly, RTL design allows the designer to describe the system in a way that is independent of the specific hardware that will be used to implement the system at a later stage. Thus, RTL design is said to be grossly process technology independent. If you observe here the microarchitecture of 8051, then you will understand that there are so many connected blocks here. All these connected blocks, say different blocks exist here. So one is CPU, another is flash memory, and another RAM and IO ports and interrupt controllers and all that. So here there are different blocks where data transfer happens, and there are control modules, and there are input output ports, so and processing units. So all these things need to be represented on part of the system. So if you observe further, a large system cannot be implemented in an RTL design so easily. So the big block such as this one will be divided into multiple segments for ease of making. So they are subdivided until they are easy to make and develop, and hence to test also. So if you see further, you will observe that this each module is actually connected, is made into a state machine. So if you observe here, each module of this is made into a state machine, where here the state machine, it will have specific triggers based on which it will move from one state to another. Okay, and here also based on this state, for example, this specific state will move from here to here based on specific trigger. So same trigger may occur between these two, but based on where the state is, it will move to the next one. So that is why the current state and the input values or triggers will determine the next state, and that state is unique. That is why this is called a finite state machine. In the same way, if you take our human behavior also, we will have specific state like a sleep and awakened state. All these states are unique, and we will not be simultaneously be in the sleep and awakened state. And if you see here, in the undergraduation, we have studied the state machine in terms of Mealy or Moore machine. So here there will be some inputs and combinatorial circuits, and it will have an output. And based on the next state and other things, the data will be stored in the register, and then it will again be sent as a present state to this. Then all these things will be evaluated, and then the new outputs will be generated. So this will be based on whether it is a synchronous machine or asynchronous machine. It will be triggered appropriately. So this state machine, when it was a small design and all, we used to convert this into state transition table. Okay, this is not the exact one, so I just picked up the one for easy understanding. So this state transition table, so we'll have a current state and input and the next state. and the output. So based on this one, it will be implemented, circuit implementation will happen. So there are different Karna maps to do all these things. So I'm not going too deep into it, but I just wanted to give you that we have converted the architecture into state machine, and then we brought it into design a circuit level. That means like both the combinational and sequential circuit. Okay, here you can see again some feedback coming along. So different implementation has occurred now. So this coding is possible in small designs. Okay, but if you want to make big designs, then this flow is not possible. So we need to have a different flow wherein architecture should be converted into state machine as before. That means like small modules, it should be converted into, again those modules should be further divided into tiny modules, and then those tiny modules should be made into state machine that will be made into RTL design. So for this, the HDL code is used to convert this one. So this HDL code can be written in either System C or VHDL or Verilog. For example, to understand the weather pattern in a biosphere shown here, there are various subsystems involved in it. One is hydrosphere, another is atmosphere, and another is the earth related. So all these systems will have an impact on the biosphere. So we need to understand each of the involved systems. So we need to make models that closely fit and represent each of the subsystem behavior in real time. Then we need to combine all these models and then holistically observe how all these subsystems work together, and then we need to make a weather pattern estimation. In the same way, each large and complex system such as this shown here will need to be observed. So we need to subdivide different functional blocks to understand, and we need to model each sub-functional blocks and model efficiently, and then when they are put together, we need to analyze them holistically. So we need to make different state machines for each subdivided blocks of the system, and then we need to arrive at how to analyze them in when they are working together in a system. So each of the system can have a finite number of states in a specific design mode to describe each functional block. So each functional block again has a description of the registers in the block referred to as sequential circuit and associated combinational circuit to understand and perform the logical operation of the functional block. So RTL designers use HDL to describe how functional blocks are connected to define the flow of the data to the subsystem or system. The digital system behavior, as described earlier, is realized as a state machine, which is later converted through RTL design as a set of hardware elements, which are called registers and combinatorial gates. So this design will have some hardware elements, which are some of them could be sequential elements and some could be combinatorial gates. The registers of the design are usually implemented as D flip-flops. An example is shown here. Sometimes these D flip-flops can have more ports like set or clear. So the phrase a register transfer embedded in RTL acronym refers to how the data transfer between registers, which would enable logical operations and mathematical operations on the data. The data stored in the register can be used as input to a logical operation, and the result of the operation can be stored back in another register. RTL uses HDL to code a state machine of a subsystem. So in HDL is mainly for behavioral modeling that looks lot like a programming language with variables, function calls, logical statements like if then else and case, and boolean statements and mathematical operators. However, HDLs are specifically designed to describe the behavior and structure of electronic circuits. So one thing that sets HDL apart from programming languages such as C, C++, and Python is that the concept of time is included within the HDL coding. This is the greatest difference. So that system operations can be triggered by clocks in the circuit, thus facilitating concurrent behavior to represent multiple flops working on trigger of the clock at the same time. So here if you observe, the clock will be coming here, and this is the clock tree we are talking here, and it will be feeding set of flip-flops. One flip-flop is shown here. So this contains 4 flip-flops. Like that here many flip-flops. So uh, once the clock triggers, several flip-flops get triggered at the same time. So these flip-flops again will have some combinatorial gates, and the final combinatorial gate, whatever that logical operations, will be stored again in another flip-flop. So for example, if the clock triggers and the data starts from the flip-flop, it will go through set of combinatorial gates and then will be stored in this flip-flop, assume. So that is how the data transfers from one register to another register, one register to another register. Like that, it will transfer. That is why it is called a register transfer language. So register transfer level. So here, what we have observed is this state machine through RTL design is converted into a gate set of gates having sequential elements and some combinatorial elements. To model the behavior of the subsystem blocks, RTL design usually includes adders, multipliers, counters, memory elements such as SRAM, DRAM, like that. Okay, so that the state machine will be realized. So sometimes no, the adders or multipliers or counters may be realized by using the gates of the technology library. That is also possible. But if specific items need to be included, then the inclusion can also happen. This is how the instantiation can also happen in the RTL design. Slowly, nowadays we are also seeing more and more complex modules started getting instantiated in the RTL design itself. So, for example, synchronizer is between the cloud domain crossings from one cloud domain to another cloud domain, which are not in sync. So, and it is also SRPG cells, state retention power gating cells, cloud gating cells, power switches, in some cases as per the need. Okay, so sometimes the design doesn't need power switches. So in that case, power switches, cloud gating, all these things are not needed. So when these hard-coded cells exist, it becomes technology dependent. Okay. However, by representing these cells as technology independent, it is possible to represent RTL code as technology independent. That means, like, assume that you wanted to use SRPG cell, but you don't want it to be from certain technology. So then you don't need to mention it as a specific cell name and all. So instead you can mention one generic name for the SRPG, and later during synthesis map it to the associated one based on the specific technology of concern, because the port and everything should be matching. So thus RTL design provides a manageable way to design complex digital systems for quick studies and fast design iterations to obtain an acceptable and optimized design before delving into more complex and time consuming phases of the design process. So what it means is like you need to know that to say RTL design is basically helping. So you may be knowing there are some tools basically which we will be discussing further, like power estimation and synthesis and all those things. All say to go from specifications to for further all the way up to GDS to implementation and all. There are several steps, and if we want to go through all those steps, it will be too cumbersome and too time consuming. And instead of that, if we take major decisions as part of the RTL design, then say IP selection, these specific cells we are talking about, synchronizer, SRP, all these, if we select the required ones, then lot of the uh, big headache and will be resolved, and these are called the work with the big hammer. That step is actually happening in the RTL design phase. Okay, so this is a critical step in transforming a high level system description into a fabricatable chip. Let us consider a design started from the specification phase, and which has the corresponding architectural design existing. Say, for example, in the case of a 8051 microcontroller architecture, you will observe that there are several blocks in it, and all these blocks, important blocks, whatever is known and to be reused, all that will have some behavioral model in a state diagram. So then which will be converted into a RTL design fashion. So now what happens is like this architectural RTL design, we need to know that it should not have any coverage holes, and it should not have any X handling issues, and it should not have any clock domain crossing issues. Say, for example, it has some unintentional latches in the design by mistake of the RTL coding, or it has set reset conflicts, or it has out of range indexing. Earlier, it used to be, this used to be a big issues. So we need to use the linting tools which will read the RTL code and then figure out that there are these simple mistakes can be avoided, and there should not be any multi-driven ports, and there should not be any non-synthesizable blocks. So assume that you wanted to create some logic which is actually not synthesizable through the existing technology cells. Then also it is difficult to finally realize. And there should not be undriven nets. That means that you have created some logic and they are not going anywhere into the design. So those kind of undriven nets should be avoided. So these are simple, I would say, issues which one needs to clear it as part of the further RTL verification and validation process. Okay, so the yeah, RTL design and verification is very key, and it should be hence RTL design becomes the very milestone key stage wherein the defects have to be analyzed at the very high level, and it will be very cheap. So if you see here, the this is the IP creation or block creation and all this. So the amount of money expended and resources time taken, this will be very small. But as we go through the system implementation, post silicon validation and checking, or in the field, that means that when we have given it to the customer, the amount of cost to figure out a bug, if there is any, and then to implement and fix it, the amount will be huge, means huge. So this we need to avoid. So we need to fix it at the very early phase. So we need to fix it as early as possible. So at this phase, so that the issues want to propagate down to the customer phase. So this is one important one, and most of the bugs are actually due to the system level specifications or RTL level things have not been understood or coded well. It is also very complex as you further understand. So, and the most of the money is actually spent during the RTL design, verification, emulation, all this. This phase we will be spending a lot of time compared to the rest of the RTL to GDS implementation. So if you, that is why we will study a little bit more on the RTL verification and validation. So let us see what is RTL verification. In the case of RTL verification, we need to understand that this is basically consists of two parts. One is static verification, another is dynamic verification. In the static verification, functional simulations are, no, formal verification is done, and in the dynamic verification, functional simulation is done. So these are two different strategies, complete or mostly exclusive way of doing. Okay, and in the verification, what we wanted to basically check is, have we made what we were trying to make? Note the question clearly. Have we made what we were trying to make? That means like you were thinking something as part of the specifications. Are you making it as part of the RTL design? So this is the key thing. So this one, if we understand, then we will know that functional simulation wise, we will be able to implement the thing correctly. So as part of the static verification, this is formal verification. So there are ADA tools, both from Cadence, Synopsys, and other mentor tools. So wherein suitable tools exist, wherein they model the expectations into mathematical algorithms, and then they will evaluate the system for correctness. Okay, we will go through a little bit more in detail in the further sections. So here we will ensure that whatever is designed and whatever as part of the specifications, that is expectations, are they correct? So this is what is being checked. And in the case of dynamic verification through functional simulation, I mean, so here what is done is the input vectors are provided to the RTL design, and a test bench is created, and the expectations as part of the specifications are based on that. The corresponding input vector should yield so and so output results. So this information is also taken. So now what is expected as part of the specifications when so and so inputs are given, and what is actually obtained when the same input vectors are excited to RTL design or compared. So if there is any discrepancy, then the design, RTL design, will be checked. Okay, so this is how the static verification and dynamic verification are performed. Okay, coming to the next one, and the RTL coverage. As we have discussed earlier, there were several issues: unintended logic, expropagation issues. All these things should be handled smoothly by the as part of the RTL design. So what we need to do is, like, the RTL design should be compact enough, as only it should result in the intended logic. This is the key thing, because sometimes because of the unintended logic, if some input excitations happen, these unintended logic will get triggered and it will lead to some other functionality. So that should not happen. So we need to ensure that each set of lines of code will realize the logic which is that much and enough. Okay, so that is the main this one. And coming to the next part, validation. This is also very important. Here we are talking here about the virtual prototyping and actual implementation. Okay, so in the case of virtual prototyping, this is through emulators. So in this emulation, it depends upon the model accuracy. So how the sock design is getting realized, okay, and through a virtual prototyping, and then we will ensure that this is properly checked. So this is what is done as part of the emulation, and there are several emulators which automatically maps the RTL representation of a design to its internal programmable gate array. Okay, so then it will perform the RTL verification. So this is also one type, and then we should ensure, as much since this is a slow process, we should ensure that only the relevant portion, the new portion, and slightly doubtful portion should be kept in the emulator, and the rest of the thing we should be able to put in a different manner. So okay, either through sock or some other programmable manner we should keep it, and then we should be able to relate the hardware and software implementations, and then we should ensure that all these are working smooth. So that is the main step of emulation, and where possible we should use it to the least extent possible. Okay, and coming to the FPGA prototyping, okay, by the way, this emulation is still pre-silicon technique. Okay, in the case of yeah, FPGA prototyping, it is actually, to a large extent, you can think either it is as part of the FPGAs, and it is actually the RTL design is converted into C of gate array cells. Okay, that means like FPGA is actually acronym of field programmable gate arrays. Okay, so there are several types of logics which are available in plenty, and based on the realization of the RTL, it will be going through synthesis and other corrections. Okay, and then it will be using the already existing NAND gates, NOR gates, XOR, all these cells, which are nowadays very rich in quantity, and rich in different variety of cells. So all these things are basically making the FPGA prototyping fast, and it is now able to handle multi-million gate designs. So the checking is also more robust nowadays. So all this is somewhat, you can think it is like a more like a actual implementation, close to physical. But there are some issues with the FPGA prototyping. But these are the different ways of validating the RTL design. So yeah, before going to the power estimation, I wanted to mention a few things about the uh, uh, RTL design verification and validation aspect. So in the case of verification and validation aspect, so as I mentioned earlier, like verification means like whether whatever we are intending, are we getting that? Are we really making that? Validation means like, are we trying to make the right thing? There is slight difference. Okay, verification is, are we trying to make what we want, and validation means, are we trying to make the right thing? So I'll tell you one analogy, which is we are following unknowingly, but if we follow it uh, more thoroughly, we will have a stress-free life. Okay, so whatever we are conceptually thinking in the specifications, that is the visualization of or vision of the chip. Okay, so that is what is, you can correlate to whatever we are thinking in the mind. Now what we are creating the RTL design, you can think as like what we are telling through the mouth, that this is the design what we wanted to make, and the rest of the synthesis physical design steps and tape out, that is the actually karmana, that is like what we are actually doing. Okay, in this way what we are doing is like, whatever we are thinking in the mind, whatever we are telling through the mouth, whatever we are doing, That means like specifications, RTL design, physical implementation, they all should be in sync. That is when we will say that chip is successfully created as per the intention. So in the same way, if manasa vacha karmana, if we do the things and if we are ensuring that all these three are equivalent, then we will not have any stress in the day-to-day life. It need not be office related. It relates to anything what we are working in other parts of the situations. So that is the main thing what I also wanted you to understand and then make life a bit easy. So coming to the power estimation, so RTL design is also used to estimate the power. That means like what IC design is doing is like whatever is possible, they are putting it into checking it at the RTL's phase. The reason being, as we have figured out earlier, like if we do many fixings at the RTL design, then the cost of implementation is low. So RTL power estimation is also done at the RTL phase, and then it is also used to convert the through synthesis by taking the target uh, IP library. It is made into gate level netlist. So this one is basically so this RTL design, which is in the behavioral model, is converted through synthesis to the gate level design. So this is the main way by which RTL design is now converted into gate level design. There are registers here, here and here. There are combinatorial circuits here. So all these things are now part of the design. So this design is made into register to register transfer. So this is transferring data. Here one register to another register, it is transferring the data. So the data taken from this register is picked, some logical operations are done, here it is XOR, and then it is stored within this register. So that is why it is called the design implementation in this phase is called RTL design. These are the several references which I have gone through as part of the slides making. Feel free to go through. Thank you.